because we're in a bit of an emergency situation here, we can't cover every single little thing that we might have liked if this were just a regular face-to-face Calc 2 class. So I'm going to prioritize the most important tests for things that we will do later and for things you'll do in later classes. So the next test we're going to talk about is called the ratio test. And they start in the textbook by talking about the limit comparison test, which we're not covering. It's very powerful and useful, but the ratio test is also pretty powerful. So we're going to focus on that one. The part that we're going to focus on is trying to compare a series with a known geometric series. And we'll see what that looks like through an example. Now take a look at this series here. It might not look geometric. I mean, it's not a geometric series, but we want to think about how we can compare this to a geometric series. So without going through this entire activity, the first part here is calculating just some ratios of successive terms. Okay, because remember what we said about geometric series. You can take the ratio of two successive terms, two consecutive terms, and you should always get the same number. That's what defines a geometric series. Now, if you were to figure out what A6 over A5 was, what A11 over A10 was, what A21 over A20, A22 over A21, etc. If you were to figure that out, you would notice that there's not a huge difference in those ratios. Now, if you let K be much, much larger, what's going to happen? Well, the prediction that activity 8.3.9 is trying to lead you to is that that ratio is going to seem to always be the same, or very close to being the same as K gets larger and larger. So the question they ask is, do you agree or disagree with the statement that the series of 2 to the k over 3 to the k minus k is approximately geometric when k is large? And hopefully you come up with the answer yes. If you do think it's approximately geometric, then do you think the series converges or diverges? Well, remember, not all geometric series converge. It depends on the R. So if this were a geometric series, which we know it's not, it's close to one, it's probably closest to the series 2 to the k over 3 to the k, which is the same as the series of 2/3 to the k, which means R would be 2/3, and since absolute value R is less than 1, we have convergence. Now, this is just exploratory. There's no rigorous argument being used here, so we have to be careful. This is just an exploration. But based on this thought process, it seems like a series like this one will actually converge. We're going to use what's called the ratio test to verify that. Okay, so this part here is summarizing what I was just saying, which is ratios of successive terms, if they seem to be the same all the time, close to being the same, they're not going to be exactly the same, but if they seem to be the same all the time, then we can compare the series to a geometric series. And that's why we have this restriction where we know that this series will converge only when the r, the apparent r that we're comparing it to, is going to be between -1 and 1. Okay, so the ratio test is saying assume sum of AK is an infinite series, then the limit as k approaches infinity of this ratio of consecutive terms in absolute value is, let's call it r. If that r is less than 1, then the series is going to converge. If r is greater than 1, the series is going to diverge. If r equals 1, then the test is inconclusive. This part is the really important part here. The test is going to be inconclusive. Think about the divergence test. If the limit of AK is 0, then the divergence test is inconclusive. That's another way to think about that test. So we just have to be careful for the case r equals 1. A lot of times in math, you'll see somebody write NB on the board. NB stands for nota bene, which translates to note well. The ratio test looks at the limit of the ratio of consecutive terms of a given series. So it's asking, is this series approximately geometric? And as we reviewed earlier, one way to tell if a series is geometric is to consider the ratio of consecutive terms. So the ratio test, even though our series is not going to be geometric, we're using the test to figure out if a series is geometric to determine whether or not these series will converge. All right. So this is kind of a summary now that we're moving toward. I'm going to cross out what we are not going to be concerned with. We have the divergence test, which we talked about at length in class. That's very important and useful as a preliminary measure. You can use it to show a series diverges, but you can never use the divergence test to prove that a series converges. That was that crucial logical point that we talked about. Then we used the integral test to determine the convergence of an entire class of series called the p-series. You can use the integral test for other series as well. If the series looks like a function that's reasonable to integrate, then you can calculate the improper integral and use the integral test for that. But the main thing we get out of the integral test is the conclusions we drew about the p-series. The limit comparison test is the one that we are not talking about here. It's actually useful for these two problems in activity 8.3.10. So you're totally free to skip those. The ratio test and the integral test, if you try to use those on part B and part D, well, you're going to have some difficulty with it. Actually, part B is probably going to be doable using the divergence test. So I want you to verify that statement yourself if you haven't already. And part D, definitely you have to skip. Okay, and then the ratio test is the one we just talked about, which allows us to compare our series to a geometric series by calculating the limit of the ratio of the consecutive terms. And it's particularly useful for series that involve nth powers and factorials. Factorials is the big one. This is probably where we're going to use it the most in later sections. And then finally, there's the direct comparison test and the root test. I'm not going to be assigning you those. But there's a lot of convergence tests for series, and sometimes one test is more appropriate than the other. Sometimes you can't get a conclusion out of one test, so you have to pick another test. So hopefully by working out this activity, you'll be able to get a little bit of practice. Along with the exercises, you'll get some practice determining which test is appropriate for what type of series. All right. Once more, to review everything we talked about in this section, both in class and in this series of videos, we have that an infinite series is a sum of the elements of an infinite sequence. So an infinite series is of this form, and we're considering these a's to be any real number. The nth partial sum uses this notation, and it's a sum that stops at a particular n. And then we interpret these SNs, the partial sums, as if they themselves were a sequence, and we see if that sequence of partial sums converges. That's equivalent to determining whether or not the series itself converges. So if the limit of partial sums gives us an actual finite number, then we say that the series converges. Otherwise, the series diverges.